All right. So we're practically finishing with regression, and it doesn't mean really we have covered all topics in regression by any means, but I think I have given you enough detailed information that if you really want to do regression for your research, you should be able to find out where to look. The only message I'm going to say is the techniques we discussed, they're not even remotely the state of the art. Okay? Not even remotely. Okay? They are just intro to Bayesian regression. Okay? So, but I think the concepts that have been we discussed basically in the development of these models are very general. Okay? All right, so what I want to do is to finish this presentation on Bayesian regression models. I wanted to go back to these hierarchical Bayesian models and explain how we're going to compute the hyperparameters that they come in the prior models in the context of our regression analysis. And I'm going to take actually the early notation from Bishop's book. Right, so I want to remind you some of the notation. You can do the same things with all the regression models we discussed, but I'm going to take the simplest. So I'm going to remind you all the notation. What you see here is the likelihood model. You remember the mean function, that's the regression function in terms of parameters. Beta is the noise, is the precision. All right, so remember W, Y, the regression function. And then when we analyzed this more than a few lectures ago, we computed the posterior of W that comes to be Gaussian. Okay. By the way, we use a Gaussian prior model for W. Remember with precision alpha. All right. So the likelihood was Gaussian, and we used a prior model for W that was also Gaussian with precision alpha. And it comes out that the posterior of W, given the parameter that appears in the prior and the noise precision beta, the posterior comes to be a Gaussian. This is the posterior mean, and this is the precision basically for the posterior. And this matrix phi is the design matrix that we denoted in different way. I think in the last few lectures that was our capital X. All right, but that's the design matrix phi. T is the vector of the responses at the training data, and that's our notation. Clear? All right. So again, this was our likelihood. We put a prior on W that was Gaussian. The posterior for W came to be Gaussian. This is the posterior mean, and this gives me the posterior variance. I want you to remember the notation. Basically, Mn is used here for the posterior mean, and Sn for the posterior variance. Okay. All right. So what when you do this Bayesian model, the way we present it up to now was like, okay, fix beta, fix alpha to some values, and you hope for the best. So now what we want to do is we don't want to fix arbitrarily these parameters alpha and beta. We want to compute them, and we want to compute them using this empirical Bayes approach. And I remind you, the way you compute them is by effectively maximizing the evidence. Okay? So let me go one step backwards to see how the evidence comes forward. This equation gives you, so let's say you train the model, you compute the posterior for W for given parameters alpha and beta. So this equation here gives you the predictions at new input point little x, and the prediction is t, given the training data t bold. So look at this equation and convince me that makes a little bit of sense. So this is the predictive distribution at some new input, right? And the predictive distribution, what is it? The likelihood, given the parameters, and what is all these two distributions there together? What we're supposed to have here? To get the predictive distribution, you integrate all the parameters, right? And you multiply the likelihood times the posterior. And you notice here the posterior was split in two parts. The posterior of W given A and B, and then the posterior of the parameters alpha and beta given the training data T. So up to now, we didn't really have this because alpha and beta were given parameters. We said, take this alpha, take this beta, and hopefully it will work. But right now, we don't accept that as a good solution. We want to do something about alpha and beta. And as you can see here, we're going to take alpha and beta to be random variables as well. So when we do predictions, we're going to integrate them out. Now, I mentioned in the hierarchical Bayes formulation, right? You started with a prior model, and you put a hyperparameter there. Somehow, when you do this hierarchically, it is okay to actually go and fix these parameters alpha and beta with some point estimates, but those point estimates need to be sophisticated. They need to be such that they maximize the evidence of the data. And the approximation today, this evidence approximation will be, if we're going to use point estimates for alpha and beta, what are the best point estimates to use? So if we do use point estimates, this big integral for the predictive distribution becomes an integral in W, where you notice now I have beta hat and alpha hat, which are going to be some point estimates to be computed. Okay? And we will discuss exactly how this computation is going to happen. So again, this would be the full Bayesian way to do things, but it's very complicated. So we're going to fix alpha and beta to some point estimates, and we're going to have to compute these point estimates. And the way we're going to compute them, we're going to take these point estimates to be the mode of the posterior distribution of alpha and beta. So in other ways, if we can compute a posterior distribution for alpha and beta, then the point estimate would be the most probable values of alpha and beta, which is the mode of that distribution. Obviously, this is not an easy thing to compute, right? So we will see how this goes about. So this is the posterior of the parameters alpha and beta given the training data, and we write this as the likelihood times the prior. And you notice in this equation on the top there is no W, right? There is no W in where W has been integrated out. So when I say the likelihood, that's really the marginal likelihood of W integrated out. So the regression coefficients are integrated out. So what we're going to assume in this empirical Bayes approximation is, because we don't really have much information about alpha and beta, we're going to take this prior to be uniform. Okay? And if this prior is a uniform distribution, really maximizing the posterior of the parameters alpha and beta is the same as maximizing the marginal likelihood. And that's why this is called the evidence approximation, because to compute the maximum, the alpha and beta that maximize this distribution, it's really approximately the same as maximizing this evidence of the training data T given the parameters alpha and beta. So the objective today is to actually compute this evidence of the training data given the parameters alpha and beta. So we need to compute this as a function of alpha and beta and somehow maximize that function to find alpha hat and beta hat. Okay? So I'm going to summarize again, right? This is the last time we're going to see this hierarchical Bayes thing in this course. I'm going to assume that from now on, somehow you can navigate through the literature. To do predictions, you need to know the posterior, right? So instead of integrating alpha and beta with the posterior there, we're going to approximate alpha and beta with point estimates, okay? And the question is, which point estimates? And the answer here is the ones that maximize the posteriors of alpha and beta. This is the marginal likelihood times the prior, and if the prior is uniform, maximizing this is the same as maximizing that. And how do you compute now this? Obviously, because there's no W, somehow you need to bring W back in the picture, because likelihood without W, you cannot write it down. All right? So look at this equation on the top and tell me if you agree with me that this marginal likelihood for given alpha and beta is this integral. So what I have done here, basically, you know what? I said, look, I have a distribution of T given alpha and beta would be the same as the distribution of T and W with W integrated out, and then I write this joint distribution as of T given W, and then the prior of W. Can see? So this is not a posterior, this is the prior. All right? This is the prior. So do we know this? Do we know these two distributions? Of course. If you know W, right? The likelihood, I'm going to give it to you explicit, is a Gaussian. All right? So I put all the terms together here with some energy term, but this is a Gaussian. This is also a Gaussian. This is written here. So actually, this integral, hopefully, we can compute it in closed form solution. So let me give you how it's going to look like. The posterior is basically the integral of what you see here, where E is basically, this comes from the likelihood, and this comes from the prior. These are familiar terms, right? Hopefully you remember more or less, okay? And I write this using these error functions, or energy functions if you like. E subscript D is basically the error of the regression function, how much away you are from the training data. And this comes from the regularization, so it's a function on a W, and this is what we use, right? So this term here in the exponential, and this is from the prior, and this term is from the likelihood. So this is what it looks like. And I can write this, if you manipulate it, I can write this as this error function calculated at the posterior mean, plus this quadratic term of W minus Mn transpose A times W minus Mn, where A is equal to that. You maybe don't remember this expression, but in the last two lectures, when I was writing the likelihood, I actually used this expression. The notation was, the symbols were a little bit different, all right? But this is a nice expression because it gives you this exponential there, this error, as the error if you select the parameters to be at the posterior mean values, plus basically this quadratic that is, W minus Mn, okay? That's what the term that comes there. So this is what you see here. There is nothing, I multiply likelihood prior, and I put them together, and it gets to this nice form, E of Mn. There is no W here anymore, and then plus this quadratic on W, and this matrix A is alpha times I plus beta times V transpose phi, okay? You can actually, if you're curious, this matrix A, it is actually the second derivatives of this error function with respect to W. It's the Hessian. And if actually you're even further curious, what type of approximation this equation reminds you, and in this case it's not an approximation, it's exact. But in general, if you have another problem and you try to write this, the likelihood times the prior as e to the minus something, and that something looks like this, what type of approximation it reminds you? That I told you is standard basically in statistics. How do we call that approximation? The Laplace approximation. You remember? Right? We approximate things with a quadratic there, and we put the Hessian in. So in this case, it's exact. All right? In this case, it is exact because basically the two distributions were the Gaussians. Okay. So we plug in the exponential to be e to the minus e, compute at the posterior mean, so that there's no W there. And then I have this exponential quadratic, and I have to do an integration on W. So immediately I'm trying to think, can I make this exponential to look like a Gaussian? So because I know how to, to marginalize I know the normalization factor in a Gaussian, and immediately you can see that this actually is nothing else but 2 pi to the power m over 2 times the determinant minus 1/2. Tell me from where this thing comes from. So I claim that this whole integral is this. From where did that come from? Remember how many parameters we have in our model, or W we have m, all right? So where is the 2 pi m over 2 comes from? Times the determinant minus 1/2. This doesn't remind you a Gaussian centered around Mn with precision A. So what's the normalization factor of a Gaussian? This, right? Okay, so basically, so this is non-analytically, so the marginal likelihood, you know, you have this, we have this from the normalization of the likelihood in the prior times this integral, and that integral is basically this times the determinant. So if you take the log, we're done. That's the evidence, right? That's the log evidence. All right, that's the marginal likelihood as a function of alpha and beta. And now the task is to compute the point estimates by maximizing this likelihood. By the way, we already have seen this equation. You know where we have seen this? Because we already discussed this. Where did this equation come from? Or equations that look like this? You remember when we were talking, finding the likelihood of the data, you know, all of this, and we talked about model complexity and model selection. They were all based on this marginal likelihood, and lots of these calculations were looking like this, okay? So what you see here is the most trivial case for our simple regression model, all right? So we have alpha and beta coming in multiple terms. So alpha comes here, beta comes there. If you look at E computed at Mn, E computed at Mn involves both beta and alpha. So there's both beta and alpha there. And then we have a nasty term, log of the determinant of A, and I remind you the determinant of A is the determinant of this, and that involves both alpha and beta. So we're going to have to find the derivatives of a determinant with respect to this alpha and beta. Sounds difficult, it's not. So let's start the algebra, but before we do the algebra, let's say if you go and plot this, marginal likelihood, how is it going to look, okay? So in this particular problem, if you plot it, let's say, and I don't even plot it as a function of alpha and beta, I plot it as with respect to the order of the polynomial. And so if you plot it in the context of M, you can see immediately what polynomial in your regression you need to use to maximize the marginal evidence. And in this case, the polynomial comes to be of order 4. Because you remember, how do we control complexity? Maximizing the evidence, if you plot it for a given alpha and beta, it is for a polynomial of order 4, and that's what you need to select in this particular data set. So this calculation, I'm doing it with constant alpha and beta, right? So we have to go back and discuss on how to maximize that evidence with respect to alpha and beta. If you don't want to do the evidence, what people actually do, and I already discussed this, right? They compute for different order of polynomials the training error, and then they compute the test error. And when the test error starts blowing up and going up, they say, that's my order of polynomial. But notice something. This standard way of computing the complexity of the model is not very, sort of, definite on what is the proper order of polynomial, because both the training and the test error don't usually change for a huge order of polynomials, from like polynomial order 3 to polynomial order 8. So what do? I mean, I suppose the best thing to do is take 3 and stop there, okay? But there's one value that you get. The evidence is maximized, m equal to 4, done. Nobody will question it, okay? All right, so let's discuss on how you do this derivatives with respect to alpha and beta. The calculations, by the way, would be identical if you have a much more complex problem, and it doesn't have to be regression. So, if you follow the algebra, you will see that things are not as complicated. And actually, when we get the final results, there is intuition actually on how the final results look like, which tells you that it's not just mathematics. There is also some common sense, basically, on the type of results we will get. So let me, to be able to do my calculations, what I'm going to do is I'm going to phi transpose phi. I'm going to define for the matrix beta times beta transpose phi. I'm going to define the eigenvectors u and eigenvalues lambda. Okay? So let's say you do the eigenvalue problem, and at least conceptually, we compute the eigenvalues lambda and the eigenvectors u. So the matrix, that Hessian matrix we had, because here we only had alpha times the identity matrix, the eigenvalues of that matrix would be alpha plus lambda I, the eigenvectors would be the same. Okay? So remember that the eigenvectors from now on of A are basically alpha plus lambda I. Now, why do I care about the eigenvectors? Because look, you have to take derivatives of this, the log of the determinant of A with respect to alpha. And a nice way to write the log to write the determinant, you know what it is to take the product of the eigenvalues. Does resonate from anything in previous life? All right, so to find the determinant of a matrix is really the product of the eigenvalues. So really, you have the log of the product of this, and you have to find the gradients with respect to alpha, and you just differentiate the logs, and there's the answer. The answer is summation over I for all the eigenvalues that you have of 1 over lambda I plus alpha. So, so this term is not painful because the answer is this nice summation. Okay. There is derivative with respect to alpha here, derivative with respect to alpha in here too. Okay, so let's put the whole things together, and if you so the other terms don't provide any complexity. So if you put all the terms together, what you get at the end is, let me concentrate on this final equation. You get the following equation. You get the optimal alpha is defined as alpha times mn transpose mn, and remember mn is the posterior mean, is equal to the summation over I of this ratio of lambda I divided by lambda I plus alpha, and I'm going to call this term gamma, okay? Because there's going to be a physical meaning actually that we're going to assign to gamma, and you will see shortly what that is. Now what you see here is something that is very common in this type of problems. We want to find so the optimal alpha satisfies this equation, but you know what? Alpha is involved in the definition of gamma, and alpha is involved inside Mn. Right? Is it alpha somewhere in Mn? Because Mn has the matrix A. So effectively, the only way you can solve this equation is iteratively to self-consistency. Okay? And you remember when somewhere in the homework 1, by accident or not, one of the TAs gave you homework to do an MLE, and you had to do some iterations. This is not very much different, basically. Okay? So the idea here is you assume gamma. I'm sorry, actually, the easiest thing is assume alpha. If you assume alpha, you can compute gamma, you can compute Mn, then you get a new alpha. For this new alpha, you get a new gamma, a new Mn, and you keep iterating, and this hopefully will converge. All right, so this is the implicit solution for finding the point estimate of alpha that maximizes the marginal likelihood. It's not necessary to do through all the algebra, right? If you take derivatives with respect to beta, it's basically very easy, okay? So it's sort of the same type of ideas. There is only one trick you need to do, okay? Remember that lambda I were the solutions of this eigenvalue problem. And because we are going to take derivatives with respect to beta, notice from this equation that lambda I changes proportional to beta. So if you double beta, lambda I will double, all right? Which means that the derivatives of the eigenvalues with respect to beta, they are really proportional to lambda I over beta. Okay, so basically you have to use this little equation, and apart from that, what you get is, you get this nice formula at the end of the days. And so the optimal beta is basically 1 over n minus gamma, summation of the square error that you're doing in matching your training data Tn, and this is your regression function with coefficients computed at the posterior mean. So this looks, it looks right like you know, like what's the word that I want to say here? It looks very much like a sampling variance, right? When we train a Gaussian, the only difference here is the error is defined here, right? Not surprisingly. And the other huge difference is that in the denominator, we don't have 1 over n, we have 1 over n minus gamma. So maybe you guys can help me figure out what the meaning of that gamma may be at the end of the day. Because you remember, for example, when we were doing the MLE estimate for this variance of a Gaussian, and you wanted to define an unbiased variance, what did we have on the denominator for the unbiased variance? 1 over n minus? I heard it. 1. And you remember we said that 1 was because we had fixed the MLE estimate for the mean, all right? So 1 degree of freedom was taken away. So when you see here 1 over n minus gamma, can you tell me what the physical meaning of that gamma, what gamma may symbolize at the end of the day? Remember that I have m parameters to fix in this problem, all right? But here I have somehow a gamma. So what gamma may potentially imply? The number of parameters that the model will be capable of actually fixing. The other parameters will not be relevant to the model, and the prior is going to set them equal to 0. So this gamma is really the effective number of W's. The effective number of W's. Okay? So gamma comes to be the effective times, the effective number of the parameters. And again, this equation on computing beta also has to be solved iteratively, not surprising there. And I wanted to give you sort of, this is a very sophisticated slide, has a lot of details, but if you get it pictorial, or if you go home and you look at all the details of the slide, things may click, okay? So let me present it without any equations, even though I wrote the equation so that you know that things that don't come arbitrarily, okay? So think of this being the likelihood. Remember, the likelihood is the MLE estimate is really is solving this least squares problem, right? Minimizing this square error, all right? And the contours of that they're coming out of the ellipse for different values of the parameters W are these ellipses, because it's a Gaussian, okay? And actually, I'm writing this in 2 dimensions, and using the directions, I am doing this plot using the eigenvectors of that matrix that we discussed before, alpha I plus beta, beta transpose phi. And so in that direction, the axis of these ellipses are basically oriented towards the eigenvectors that we discussed. And the axis, this is 1 over the square root of lambda 1, and this is 1 over the square root of lambda 2. So the eigenvalue lambda 1 here is the smallest, and lambda 2 is the biggest. Okay? So I'm doing this again in 2 dimensions, and this is the MLE estimate of W. All right? It's basically the W that minimizes this error. This is the MLE estimate. Now, somewhere we have also a prior, and the way I want you to think about the prior, right, in computing at least the map estimate, is like minimize this problem, but actually try to satisfy this constraint that W is less or equal to the values on this contour. All right, so you constrain W, transpose W to be within this contour that you see here, and that what it does is it pushes the MLE estimate towards the prior, and this is the map estimate, just in a generic sense. So what if you, so the equation that you see here, all right, I rewrote the map estimate, this is the posterior mean, okay? I'm sorry, it's the mode of it's a Gaussian, it's the same thing, right? Is the posterior mean I wrote it explicitly in terms of the MLE estimate, okay? And if you express this in terms of the eigenvectors and eigenvalues, really the equation you're going to get is that W map, okay, is really summations of the eigenvalues lambda I divided by lambda I plus alpha times these coefficients Wi, the MLE coefficients. I mean, if you write this equation basically, right, in terms of eigenvalues and eigenvectors, you can immediately see that you get eigenvalues from this term, you get lambda I plus alpha inverse, so you get this in the denominator, and from this times phi transpose phi, you get lambda I, all right? So you get a relation between the map estimate and the MLE estimate looking like this equation. Basically, you know, you can originally pick with these plots, they look like that. And what I want you to visualize here is the following. If we take the eigenvalue lambda 1, that is the smallest, so if lambda 1 is very small, okay, this whole coefficient becomes, what happens to this coefficient when lambda 1 goes to 0? It goes to 0, which means what? That the solution to this problem is the map estimate is equal to 0. So effectively what it means is, for the small eigenvalues, the data cannot actually tell you what W is because W doesn't play any role in explaining the data. So what then happens, the prior comes and pushes that map estimate to 0. Okay? And similarly, if you have larger eigenvalues, lambda 2, all right, so this term is significant, and the MLE, the map estimate then for lambda 2 is pushed towards the MLE estimate. That's why you see this W vertically to be very close to the MLE estimate, and horizontally to be far away from the MLE estimate because it's pushed towards the 0 value, which is the mode of the prior. Bottom line, right, what I want you to remember is, if you take this physical meaning of this ratio of lambda I divided by lambda I plus alpha, and you sum all of this together, what you get is the number of effective parameters that your model can compute, okay? And that number of effective parameters you can show, it is really between 0 and the maximum order of polynomials that you have in your model. So if you go and you throw polynomials of order m, it doesn't mean you can compute all of these coefficients, because some of them are irrelevant, and what happens is this gamma is the one that defines how many of those polynomials, of these terms, these W terms are basically needed and can be explained by the data. Okay? So this is a very nice way to reason about the effective number of parameters. Okay. All right, so I am literally done with this, right? So the so if you you know, if so in the problem in the implementation that we have, we fixed the parameter beta to some value, and in this case actually it was a true value, and then we maximize the evidence with respect to alpha, and if I concentrate on this plot, right? This, it shows the evidence as a function of alpha. You can see as a very nice distinct maximum. So no ambiguity there. Immediately you say, that's my alpha, done, and nobody will question you. And interestingly enough, when you look at the test error, it is very nice because that's sort of the point where the test error changes basically direction, okay? So this is when the test error starts growing. So this gives you a nice appealing, basically, sense on why this is a very good measure for selecting the point estimate of alpha. Now, one of my students who a few years ago when I was teaching this course at Gordon told me he tried to also do the optimization on beta, and somehow either he did it wrongly or he had some difficulties actually. he could not identify a unique beta. Okay, don't know if that's true, but if any of you is interested to actually do that optimization in beta as well, please do so, because the implementation we have, it only does the optimization on alpha, and you get this nice plot. All right. By the way, if you have a lot more data than the order of polynomials, then the effective number of parameters comes to be equal to m. All right, so you can compute all the coefficients in your polynomial, and it comes out that these two equations that I gave you that maximize the evidence, you don't actually have to iterate them to compute alpha and beta, because gamma is already fixed to equal to m, and these equations directly can give you alpha and beta. Okay, so if you have too many data, then you don't really have to worry that you will be able to compute all the parameters in your problem. All right, so let me, again, I don't have time to philosophize, right? You will need to take more courses in machine learning to learn more sophisticated ideas about these regression models. But there are issues here in these regression models. So for example, we go and say, we're going to use these basis functions for our regression function, and we do this before we even have seen any training data. So it's like you decide what model to use without knowing what model the data may ask for. Okay? The other problem is, if you try to extend these methods to very high dimensional problems, you won't be able to do it. If you try to do this in 100 dimensions, it will be an issue. Now you may say, who cares about 100 dimensions? Well, these days, I care about 5,000 dimensions. So you may not care about 100, I care about 5,000. So these methods will not be able to scale in high dimensional problems, and there are many ways to address it. Obviously, dimensionality reduction of the input is something maybe we will discuss if I teach another course next semester. And of course, there are different ways of doing these regression models, and using neural networks and deep learning introduce another direction that you may want to explore. All right, so let me finish to only, this topic is, we're not going to explore it in this class, but I want basically to throw at you an idea that's extremely powerful, that somehow, rather than doing these regression models using basis functions, maybe we can do it using what is called this kernel representation. Sounds maybe weird now, but so let me just tell you very little algebra on what this kernel representation is going to be. You remember the regression function? Do we agree? Let's take the regression function, compute it at the posterior mean. So this is my mean response. That's my regression function, right? It's phi. So if you want to find the solution at x, use the posterior mean, and it is phi transpose mn with phi compute at x. Correct? Nothing new. All right? So now what I do is, you remember the expression, the posterior mean, it was beta times the posterior variance times phi transpose times t. I just plug in the posterior mean like that. And then what I'm going to do is, I am going to write this last calculation here explicitly, because this phi transpose multiplies each of the training data points Tn. So I'm going to write this equation, this matrix equation, explicitly like that for a reason. So tell me that you're fine with this. Are you fine with that? So Tn is a scalar. It's just the value of training point n. So I wrote this phi transpose T, I expand it like that. Okay? I mean, how do you multiply a matrix by a vector? I have done it explicitly. Okay? All right. Now I'm going to name beta times phi of compute at x transpose times Sn times phi of xn. I'm going to name it as k x comma xn. so this is kx comma xn, and I call this my kernel. So effectively, if you define this a kernel, so I want you to think actually of the kernel now. It is some sort of a measure of how much the response at xn and x relate to each other, all right? And you use as a measure the distance of the points in input space, x and xn. Okay? So you take 2 points. So this can be a Euclidean distance, can be something else, right? But somehow you try to measure the response, right, by using these kernels, and you get this wonderful expression that basically tells you a way to interpret the regression function is by weighting each of the training data points with these kernel values. And interestingly enough, the kernel computed at xn diminishes in value, right? Becomes smaller and smaller the further x is from xn. Which means this value becomes significant when x is close to xn, and in that case, Tn is more significant in the prediction of x than at some point that is far away. Okay? So if you actually want to plot in one dimension how this kernel looks like, okay? So this is, here I'm plotting kernel computed at x and x prime, and you notice the kernel takes only significant values when x is very close to x prime, and it's practically zero, very small, when x and x prime are away from each other. Okay? So someone will say, wait a second, if this is correct, right, and it is correct, okay, this immediately gives me a room to define thousands of new methods for doing regression, where effectively I take the training data and I fit some kernels around those training data, and those kernels can be Gaussian, can be anything you want to, and then I basically I weight this training data, and there's my response. And more interestingly, why I wanted to tell you about these kernel methods is, you may ask the following, wait a second. These kernels here, you define it directly in terms of the basis functions. Can I actually use this expression to start with and put an arbitrary kernel there without any basis functions? And the answer is yes. That's the paradigm of using kernel methods, basically, to do regression and everything else in machine learning. An extremely powerful paradigm that leads to many new algorithms, right? So rather than actually introducing the basis functions and doing all these calculations, you now say, no, I'm going to introduce a kernel, and then basically with this kernel, I'm going to weight my training data, and that will be my regression function, and I'm done. Okay? So I am not going to bother you with kernels, but how many different kernels that somebody can use? Infinite. There are certain properties that need to be satisfied, right? But you can use Gaussian kernels. Actually, these days, these techniques are being pushed to the limit where some of these kernels are defined through neural networks. So basically, you put a lot of thoughts on how these kernels will look like to best represent the response data, especially in high dimensions, okay? But right now, I call this the equivalent kernel representation of regression models, because effectively a regression model with basis functions can be written in this kernel form, but more importantly, this kernel form can be the starting point to do regression and practically every other task in machine learning. Now, this kernel basically again like this plot, right? If you take slices of this plot, they look like that. All right, they are very small values oscillating like that, and then a peak when x is near to x prime, okay? So they're really localized. And what is interesting is, these functions, phi of x that we have here, may be polynomials, they're not localized, but when you compute the equivalent kernel, the kernel is localized. And immediately you start thinking, why should I use these global basis functions when the calculation that I do at the end of the day, it involves this localized kernels only? And that's why I told you once that the basis functions you use need to have local support, okay? Because these approximations basically, they only require this local support, okay? So if x and x prime, the idea here is you try to predict x, this kernel is only significant for the training points xn that they're close to x. The rest don't matter, which means if you try to approximate something here, only the training points that they're in that neighborhood matter, okay? And so this is very important, and it leads to very many different type of algorithms. If you actually, in the regression problem, just to give you another sort of thought for your lunch, if you take, if you remember we compute the posterior distribution for the parameters W. So if you, let's say, take, if you want to compute the covariance between the responses at, at two different points, x and x prime, and you use this covariance for W being Sn, so I am just substituting the regression functions being phi transpose W, W transpose phi at x prime. It comes out that this covariance of the response at two arbitrary points is really proportional to the kernel value. So if you want to know how the response here correlates with the response there, the information is all contained in the kernel. If you don't think of this kernel representation, I had told you the only way to capture the covariance at two different locations is to draw samples of W and then plot the regression function for different W's, and this is what these plots are all about. So this information that you see here, this variability at two different points in x and x prime, is actually the information that's contained on the kernel. Okay? And when we plotted the error bars in our predictions, these were point-wise uncertainty. When you plot like this, the samples of the regression functions, this captures correlations at two different locations. So in many ways, people plot this, but if you really need correlations, is this type of plots, okay? Let me just finish 1 minute ago. You can show, all right, and I have the calculation here, it's trivial. These kernels are really inner products, okay? So the mathematics that you get, all right, is very rigorous actually because of the kernels coming to be inner products. Okay, inner products basically means that if I want to compute the kernel, I can write it as the inner product between two functions basically. Okay, and for the regression case, this is exactly what the actual solution looks like. Now, if you generalize this concept, it leads to what's called Gaussian processes. If any of you is interested on really fitting complicated data, high-dimensional problems, you need to know about Gaussian processes. I will not cover the topic this semester. If there's anybody interested, I will offer a course on this possibly next semester, and part of it will cover Gaussian processes. Okay, it's something that I think everybody should know because there is plenty of software available out there. Okay, the starting point of defining a Gaussian process is to define a kernel. Okay, and so there are similarities with these regression functions, but you don't start with basis functions. You start with the kernel, and starting with the kernel, it's practically equivalent as using an infinite set of basis functions. Okay, so I'd also for you to think this weekend. So let me finish there. I will email you as what is going to happen on Tuesday. I am not going to be here on Tuesday, so I will see you Thursday. And I will mail you also about the office hours and about the extension of the homework. Okay? All right. So no need to panic. Okay? So I will see you next week.
特别谢谢。 I have a quick question.
So you showed us this plot. Right?
Yeah.
There are significant trends away from
Yeah.
when the x and x prime are
Yeah.
is
Yeah.
there, but
No, it's just, I think, it's just, you remember when if you plot a slide, what you get is lots of oscillations, okay? They're insignificant.
yeah, but these look very systematic.
The fact that they look, it's systematic because, as you notice, it's going up and down, up and down, up and down. That's when you get the darker areas, the darker blue and the lighter blue, etc. Yeah.
Okay, all right.
Yeah, so it's like a delta function that sort of starts like a sine function going down to zero basically at high distances.
Thank you so much.
Yep.